Hi, and welcome to a new lesson from Easy Chemistry. This is Mr. Kusai, and today we're going to start a new chapter, a new topic in chemistry, which is the chemical equilibrium. We're going to start the first lesson of this chapter, which is a state of dynamic balance. This section or this chapter is very, very important because if you understand it, you will understand a lot of next chapters in chemistry, such as the rate of chemical reactions. And also it has many questions in the exams, for example, MSAT or the ministry's exam. So let's start our new lesson. Our objectives for today are to explain the characteristics of a chemical equilibrium, to write the equilibrium expression for a system at equilibrium, and to calculate the equilibrium constant from concentration data. Look at this image here. By the end of this lesson, you must understand what it's about. All right. We have two types of chemical reactions. We have the reversible reaction and irreversible reaction. A reversible reaction is a reaction that proceeds in only one direction. The products do not react together to reform the reactants. Only the reactants, they are reacting together to form the products and finish the chemical reaction like this. An example about this irreversible reaction is when the fuel undergoes a combustion reaction. We studied this type of reaction. We call it the combustion reaction. Is when an organic compound reacts with the oxygen to form carbon dioxide and water, and it produces heat. If you look at this image, this is the burning of propane, and this is the result. It will give you carbon dioxide, it will give you water vapor, and it will give you a lot of energy. As you can see here, after the reaction occurs, the product CO2 and H2O, they will never react together to give you the CH4 and O2. That's why we call it irreversible reaction, meaning the products, they will not react together to reform the reactants. The second type of the chemical reaction that we are studying in this chapter is the reversible reaction, which is the reaction in which the conversion of the reactants to the products and the conversion of the products to the reactants, they occur at the same time. So not only the reactants react to form the products, but also the products can react to reform the reactants again. In the irreversible reaction, we use one arrow from the reactants to the products. But in the reversible reaction, we use double arrow, one from the reactants to the products and the other one from the products to the reactants. An example about a reversible reaction is the producing of ammonia. Ammonia is very, very important, and it's produced in many countries. One of them is the UAE. There are many factories in Dubai, for example, and they are producing this important gas. As you can see, the ammonia, it has many uses. For example, we use it to produce the ammonium nitrate, which is very important compound. Filterization, urea, also for explosive fibers, ammonia sulfate, and many, many uses. As you can see, this factory here is in Dubai, located in Dubai. And what is happening here, this factory, and what is happening here, this is the ammonia molecule. As you can see, it has nitrogen here. It has 3 hydrogens, as you can see from the chemical reaction. So, and it's produced from 3 hydrogen molecules and 1 nitrogen molecule, N2 plus 3H2, as you can see, 3H2, and they produce 2 molecules or 2 moles of the NH3. If you check here, this diagram, you will find that because the hydrogen and the nitrogen are reactants, so the concentrations versus the time, the concentration of the hydrogen is getting reduced, the concentration of the nitrogen is getting reduced, and because we have 3 moles of hydrogen, 3 more molecules than the nitrogen, that's why the concentration of the hydrogen is greater than the concentration of the nitrogen. And then they are producing by the time the NH3, the ammonia. But in the initial of the reaction, initially, there is no concentration of ammonia, NH3. That's why we start the concentration from 0. And it starts to increase all the way to here. And all the 3 concentrations now, after this line, they are constant. The concentrations are constant. So this reaction, basically, we cannot write it in one arrow, because what is happening, that after producing the NH3, the ammonia gas, it will decompose to give the hydrogen gas and also the nitrogen gas. So there are 2 reactions that are happening at the same time. The forward reaction, which is the nitrogen plus the hydrogen, gives you the ammonia. At the same time, the ammonia is decomposing to give you the hydrogen and the nitrogen. To write this chemical reaction, which is a reversible reaction, we use the 2 arrows, as you can see. The first arrow, this arrow, from the reactants to the products, we call it the forward reaction. And from the products, when they decompose or they react again to reform the reactants, we call it the reverse reaction. So, products or reactants, we start from the highest concentration, as you can see, and they start to be reduced, and the products are forming. They start to be formed all the way like this, and then the products start to decompose, or the products will react again to give the reactants. So it's going to be like this until they reach to a point where there is an equilibrium or balance, or the reaction will stop at this equilibrium, basically at this line, where the concentrations of the reactants and the products are constant. Here we have constant concentrations. And here where is the equilibrium? So at equilibrium, the concentrations of the reactants and the products are constant. All right, we have something called the law of chemical equilibrium. What is meant by a chemical equilibrium? It's a state in which the rate, which means the speed of the forward reaction, equals to the rate of the reverse reaction. They balance each other. That means if we look here at the forward reaction and the reverse reaction, we reach the equilibrium state where the forward reaction, the rate of the forward reaction and the rate of the backward or the reverse reaction, they equal each other. And this is the equation here. Rate of the forward reaction equals to the rate of the reverse reaction. Now, the law of chemical equilibrium, it states that at a given temperature, a chemical system might reach a state in which the ratio of the reactants and the products concentrations are, or they have, a constant value. For example, if we have this reaction here, A is the number of moles of A in a balanced chemical reaction. B is the number of moles of B, and these 2 are reactants. C small is the number of moles of C, and D small is the number of moles of D, and those are the products. This is a reversible reaction because we have double arrow. We have the forward reaction and we have the reverse reaction. Therefore, the constant, as you can see here, we said the products and the reactants ratio is constant. It has a constant value. So the constant here, it equals to the concentration of C to the power of its number of moles multiplied by the concentration of D to the power of its moles. So basically here we have the products, each one to the power of its number of moles in a balanced chemical reaction, divided by the concentration of A to the power of A small multiplied by the concentration of B to the power of B small, and those are the reactants. So always here the products and here the reactants, each one to the power of its number of moles. All right, let's go back, for example, to this reaction here. N2 plus 3H2 yields to 2NH3. What is the K, or the constant of the equilibrium of this reaction? First of all, it's a reversible reaction. Number of moles of nitrogen is 1. For the hydrogen is 3. For the ammonia is 2. And this equation is balanced. Here we have 2 nitrogen atoms. Here we have 2 nitrogen atoms. Here we have 6 hydrogen atoms. And here we have 2 multiplied by 3, 6 hydrogen atoms. So we're going to write it like this. The concentration of NH3 to the power of 2 divided by the concentration of nitrogen to the power of 1 multiplied by the concentration of H2 to the power of its number of moles, which is 3. So this is the equilibrium constant expression for this chemical reaction. And that was our second objective, which is how to write the equilibrium expression for a system at its equilibrium. Let's check this example here. How to calculate the equilibrium constant. We have this chemical reaction, which is H2, which is a gas. It reacts with I2, which is also a gas, and it will give you a reversible reaction, HI, which is also a gas. First thing, we need to balance this chemical reaction. We have here 2 hydrogens, 1 hydrogen, 2 iodine, 1 iodine. So I'm going to multiply the HI by 2. Now it's balanced. To write the expression, as you can see here, the KEQ, or the constant of the equilibrium, or equilibrium constant, it equals to HI to the power of 2 divided by the concentration of H2 multiplied by the concentration of I2. In these trials here, you are giving the concentrations, different concentrations of H2. This is trial number 1, trial number 2, and trial number 3. We are changing the concentrations of H2 and I2. And every time you are changing the concentration, you are having a new concentration for HI, which is the product. See here? Different concentrations. So basically the 3 of the species, we have different concentrations for them. When we apply the KEQ, you will find, after you calculate it, and you guys can check the answers, you will find that KEQ is constant. No matter how you change the concentrations, it's always constant. 49.7, 49.7, 49.7. The only thing that change this value of AQ is when you change the temperature. So the equilibrium constant at a constant or at a given temperature is always constant, as you can see for all reactions. All right, let's now apply what we understood by solving some problems. Calculate the value of KEQ for given concentration data on one equilibrium position, and you are given NH3, N2, and H2. Basically, this question, it came in exam 2019. and you are not given the chemical reaction, because this chemical reaction is very important to memorize and understand actually. So how can we write the chemical reaction? H2 plus N2, a reversible reaction which has 1 mark, yields to NH3. For writing the chemical reaction, you don't have any mark. But for writing the balanced chemical reaction, you will have 1 mark. So H2, we have here H2 and we have here 3H. So we're going to multiply this one by 3 and this one by 2. Now the H's, I have 6 and we have 6 here. Nitrogen we have 2 and nitrogen we have 2. That was the first step. Number 2, K equilibrium, we need to write the expression for the equilibrium constant, which equals to products always over reactants. Each one to the power of, or raised to the power of, the number of moles in the balanced chemical reaction, or the stoichiometry in a balanced chemical reaction. The products are NH3. The number of moles is 2, so to the power of 2. The reactants are N2 to the power of 1 and H2 to the power of 3. Now all you need to do is to write the numbers, compensate the numbers for each species. So for NH3 is 0.933 to the power of 2, divided by, for N2 is 0.533 to the power of 1, multiplied by, for hydrogen is 1.600 to the power of 3. And using now calculator, you will find the answer is 0.933. You can guys help me with the calculations. And it's going to equal to 0.398, or it equals to 0.4 if you round it. So this is the excuse me, this is the K equilibrium for this reaction. Problem number 2, I would like you guys to pause this video and try to solve it by yourselves. All right, calculate the K equilibrium for the following reaction using given concentration data. And basically they gave you the chemical reaction here because you don't need to memorize this reaction. And you have the concentration of CO, concentration of H2, concentration of CH4, and concentration of water. Before we start, there is very important thing. In the equilibrium expression, or equilibrium constant expression, we only write the gases and the aqueous. So whenever you have the gases, we can write the equilibrium or the concentration for them. For the aqueous solutions, also we can write the equilibrium. But the concentration of any solid, for example, if I have A, which is solid, that means it's going to be constant concentration. Also, the concentration of B, if it was liquid, so it's also, both of them, they have constant concentration. That's why we never include the solid and the liquid in the expression of equilibrium. We will study that next lesson in details, in more details. Here we have all of them are gases, so I'm going to write the K equilibrium for this reaction equals to concentration of CH4 multiplied by the concentration of H2O. And as you can see, H2O in this case is a gas, not liquid. If it was liquid, then we never write the concentration of H2O in this expression. And they will not give you the concentration of H2O because it's already constant. Divided by the concentration of CO multiplied by the concentration of H2, and it's to the power of 3 because the number of moles of H2 is 3, which equals to, we compensate now the numbers in this equation. It's going to be for CH4 is 0.0387 multiplied by, for H2O is 0.0 also 387 divided by the concentration of CO, which is 0.0613, multiplied by the concentration of H2, 0.1839, but to the power of 3, using the calculator to calculate this. And the answer should be 3.928. I hope you guys learned something new today. If you have any questions, just write it in the comment. I will answer all the questions. Have a nice day. Bye bye.